myself was a BSc student. I had attended a summer school in RRI, and just like you people sitting there, I had sat through the lectures of many eminent professors of that period. And it was a summer school in physics, not in astrophysics, but two students from that summer school turned out to be astrophysicists. One was me, and the other was Tanu Padmanabhan. So many of you might have known his name. So this RRI summer school led to a lifelong friendship between the two of us, which ended only on the day when I received the shocking news that Paddy was no more among us. So anyway, the organizers have requested me to give 2 lectures on the sun. The astrophysical study of the sun involves 2 aspects. One is the sun as a star, and another one is the solar activity. So what are these? So by now you would surely know that stellar structure theory is one of the pillars of astrophysics, and by solving equations of stellar structure, we can calculate how density, pressure, temperature, etc. would vary with radius inside a star. Now physics and astrophysics, these are experimental sciences. So when we develop some theory, we would always like to experimentally verify that theory. So is it possible to experimentally verify the stellar structure theory? So if we solve the equations for a star of 1 solar mass, then what we get is known as the standard solar model. And during the last few decades, as a result of some remarkable developments like this helioseismology, study of solar oscillations, and also solar neutrino experiments, it has been possible to establish that this standard solar model is a remarkably good model. It agrees with the interior conditions of the sun. But if you come out of the interior, if you come to the surface and the surrounding regions, then you surprisingly find that there are phenomena which cannot be explained with stellar structure theory. So according to stellar structure theory, a star should be a spherically symmetric object, and at the radius of the star, its density, temperature, etc. should go to 0, and there should be nothing beyond that. But in the case of the real sun, we find phenomena like sunspots and solar flares, which cause a departure from spherical symmetry, and even above the sun's surface, we find the solar corona, which is much hotter and highly non-symmetric. So all these phenomena which collectively make the sun much more complicated than a simple textbook star, these phenomena are collectively known as solar activity. So in the within the last few years, we have become aware that many other stars also have a similar activity. There are big star spots and stellar flares. So in view of the fact that I have very limited time, and you all have already heard lectures on stellar structure from Professor Srinivasan, so I decided that I shall skip the subject of sun as a star completely and mainly focus my attention in the subject of solar activity. So one of the major realizations of 20th century astrophysics has been that the magnetic fields of the sun, that has been behind all these different aspects of solar activity. Let me begin by showing you a photograph of iron filings around a bar magnet and compare with it a photograph of the solar corona taken during a total solar eclipse. Just as the iron filings are tracing out the magnetic field lines of the bar magnet, you get a feeling that this hot gas in the corona is tracing out the magnetic field lines of the sun. And now we know that to be the case. So looking at this photograph, you may think that solar magnetic field is something so beautiful that we would like to study it, even if there is no practical benefits from it. But I at first want to tell you that there are also some very practical reasons why we should study the solar magnetic field. So on March 13, 1989, about 6 million people in Quebec in eastern Canada woke up in the morning and found that their homes were without electricity, which could be restored only after 8 hours. Now in Bangalore, if I wake up in the morning and find that there is no electricity, perhaps I would not be too surprised, but it was not usual for citizens of Canada to go without electricity for 8 hours. So what could have caused that? It seemed that 4 days before, solar astronomers had seen a large explosion on the sun known as a solar flare. So here is a movie of a solar flare, and they occur above sunspots. So we are going to discuss very soon that sunspots are regions of strong magnetic field, and these flares are also caused by these magnetic fields. The energy of a major flare can be as high as 10 to the power 26 joules. So for comparison, remember that the atom bomb which destroyed Hiroshima had the energy of 10 to the power 14 joules. And usually 3 or 4 days after a major solar flare, we often see beautiful polar aurora. So that is one of the benign manifestations of a solar disturbance. But there are several more damaging effects of solar disturbances. You know that we can communicate by radio with distant continents in spite of the curvature of the Earth's surface, because the radio waves get reflected from the ionosphere. So after a major solar disturbance, the ionosphere gets affected, and that may disrupt radio communication with faraway places. And the solar disturbances also can damage electronic equipments in man-made satellites unless expensive precautions are taken, and they can trip power grids like what happened in Quebec in eastern Canada. And I should mention that the effects of solar disturbances are felt maximally near the geomagnetic poles. So that region of Canada is vulnerable because it's very close to geomagnetic poles. And nowadays we have many airlines flights, especially the flights going between Europe and North America, which come very close to geomagnetic pole. So after a major solar disturbance, these routes become very dangerous. So, so often these airlines companies have to reroute these flights, costing much more in aviation fuel and taking much more time. So because of these effects on solar disturbances, we would like to know when solar disturbances are more likely to occur. So as I already pointed out that the solar flares occur above sunspots. So when there are more sunspots on the sun, more solar disturbances are likely to occur. And in 1844, Schwabe discovered that the appearance of sunspots on the solar surface obey a sort of periodic pattern. So here is a plot of number of sunspots seen on the sun as a function of time during the last 400 years or so. So the early entries here just after the year 1600, they were based on the records left by Galileo and some of his contemporaries. And after that, there was a period of about 80 or 90 years known as Maunder minimum, when sunspots were not seen at all. And after that, the sunspot number has gone up and down in a roughly periodic fashion with a period of approximately 11 years, although there are lots of irregularities. And we have more solar disturbances when the sunspot cycle is at its peak. And these affect us So we can say that this sunspot cycle is nature's third most important cycle for us after the cycle of day and night and the cycle of seasons. And we also have the evidence that this sunspot cycle affects the Earth's climate, though we still have very poor understanding how exactly that happens. For example, during this Maunder minimum, it's known that the Earth was somewhat colder. So of course, that was before the regular records of temperature started being kept. But that was a time when landscape painting was very popular in many regions of Europe, and some of the well-known landscape painters have left us paintings showing many this type of frozen canals and frozen rivers which do not freeze nowadays, indicating that it was a time of unusual cold climate. And perhaps this is a time for a sort of commercial break. I may mention that I have written a popular science book which explaining both the phenomenology of the sunspot cycle and the physics behind it. And since it's printed in UK by Oxford University Press, its price is maybe a little bit high for Indian students, but at least Amazon India is selling a Kindle edition which is perhaps affordable. And also organizers of this meeting said that they are trying to get a couple of copies of my book so that you people can look at it if you are interested. Okay, it was in the year 1908 when this astronomer Hell took the spectrum of a large sunspot and found the evidence of Zeeman splitting. I suppose all of you have learned about Zeeman effect in your college classes. Okay, so from the Zeeman splitting, Hell concluded that sunspots are regions of strong magnetic field of about 0.3 Tesla, approximately 5,000 times stronger than the magnetic field near geomagnetic poles. And I would say that this was a momentous discovery in the history of physics, because this is the first time somebody conclusively established the existence of magnetic fields outside the Earth's environment. Now we know that magnetic fields are ubiquitous in the astronomical universe. Most stars, planets, and galaxies have magnetic fields. And with this discovery, it also became clear that the 11-year sunspot cycle is essentially a magnetic cycle of the sun. And about a decade after that, Hell and his collaborators made another very important discovery. Often we see two large sunspots side by side, as we see here, and here the size of the Earth is indicated to give you an idea how large the sunspots can be. And Hell et al. Found that in the cases of such pairs of sunspots, usually the two sunspots have opposite magnetic polarity. If one is positive and the other is negative. So the most plausible explanation for it is that there must be some strand of magnetic field underneath the sun's surface going like that, and it's popping out from the surface in this manner. So if these two intersections with the surface become the two sunspots, then in one sunspot you have magnetic field lines going out, making it a positive polarity sunspot, and in the other sunspot you have magnetic field lines going down, making it a negative polarity sunspot. And if this is true, then we expect that the solar corona would be full of this kind of magnetic loops above the sunspot pairs. And we now know that to be the case. During the last few years, solar astronomers have developed ingenious techniques for mapping, for imaging these magnetic loops in the corona, and here you see some beautiful magnetic loops. And now I show you something which I find absolutely fascinating, a magnetogram map of the solar disk. So a magnetogram is an instrument with which you can determine the magnetic field at every point on the solar surface. So if this map is produced in this way, so if the magnetic field is positive at a point, then you put white color. If the magnetic field is negative, you put black color, and if it is too weak or undetectable, then you put gray color. So in many places you see a white patch and a black patch side by side. So these are nothing but a pair of sunspots, of which this sunspot have positive polarity and this sunspot have negative polarity. And if you look at the distribution, then you will see that in the northern hemisphere, the sunspot on the right is white or has positive polarity, and sunspot on the left looks black or has negative polarity. And in the southern hemisphere, it is opposite. The sunspot on the right has a negative polarity, and sunspot on the left has positive polarity. And it remains like this for one solar cycle of 11 years. So if you were to look at a magnetogram map 11 years earlier or 11 years later, you would find that in the northern hemisphere, this black or negative polarity would come to the right, and white or positive polarity would go to the left. And the southern hemisphere also, there would be a reversal like that. So if you only count the number of sunspots, you think that the period of sunspot cycle is 11 years, but you actually have to wait for 22 years if you want the magnetic field to come back to its original configuration. And you notice another interesting thing, that if you draw a straight line connecting the centers of this pair of sunspots, you would find that the straight line will be nearly parallel to the sun's equator, but not exactly parallel. There is a sort of a slight tilt, and we statistically find that sunspot pairs at higher latitudes like this, they have a larger tilt. So this fact that sunspot pairs have tilt, and this tilt increases with latitude, this is known as Joy's law, after Joy, who discovered it. And this is an original plot from prepared by Joy, so indicating the tilts of sunspot pairs plotted against latitude. Now, for the time being, if you forget about this tilt, then looking at this distribution of magnetic fields, you get a feeling that in the northern hemisphere, underneath the sun surface, there must be some magnetic field lines going in this manner. So if parts of these magnetic field lines are coming out, then on this side you have a positive polarity sunspot with field lines coming out, and on this side you have negative polarity sunspots with field lines going down. And in the southern hemisphere, you would have a magnetic field underneath the surface going in this way. So in other words, you expect that there would be a subsurface magnetic field which would look like this. So in the jargon of our subject, this is called a toroidal field or a toroidal component. And we believe that the Earth's magnetic field looks more like this. This can be called a poloidal field or the poloidal component. And a theory which tries to explain how magnetic fields arise in different astrophysical systems, that theory is known as dynamo theory. And in 1955, Parker wrote the fundamental paper on dynamo theory, and which he proposed a model of the sunspot cycle. So he proposed that the cycle is produced by an oscillation between the toroidal field and the poloidal field, somewhat reminiscent of the oscillation between potential and kinetic energies in a simple harmonic motion. So this was a remarkable hypothesis for that time, because at that time astronomers didn't even know whether the sun has a poloidal field. And in fact, in the very same year, 1955, Babcock and Babcock, a father and son pair of astronomers, found first compelling evidence that there is a magnetic field, weak magnetic field in the polar regions of the sun of strength about 10⁻³ Tesla, much weaker than the magnetic field inside sunspots. But is there really an oscillation between the toroidal field and the poloidal field? That could be established only after solar astronomers have gathered data about polar magnetic fields for several decades. So here I show the relevant plot. On the top, there are plots of this solar magnetic field. The solid line is for north polar magnetic field, and dashed line is for south polar magnetic field, and below it you see a plot of the sunspot number. And remember that sunspots form from the toroidal field, so the sunspot number is some kind of a proxy of the strength of the toroidal field. So you can see that the poloidal field, polar field of the poloidal field is strongest at a time when the sunspot number of the toroidal field is close to 0, and the sunspot number of the toroidal field is strongest at a time when the polar field or the poloidal field is about 0. So we really see an oscillation between the toroidal field and the poloidal field, exactly like what Parker proposed several decades earlier. So now I am ready to state what I would call the central dogma of solar dynamo theory. So the sun's magnetic field consists of both a toroidal component and a poloidal component. The sunspots arise out of this toroidal field, and the polar field, magnetic field, is a manifestation of the poloidal component. And since we have an oscillation between them, so there must be a process which for producing the toroidal field from the poloidal field, and to complete the cycle there must be also a reverse process producing the poloidal field from the toroidal field. Now our job should be to make a mathematical formulation of this central dogma using the basic principles of physics. Let me tell you how we proceed. So the material of the sun is in the plasma state, often called the fourth state of matter. You know that the Indian physicist Shah studied the process, how on heating a gas, its atoms get broken into positively charged ions and negatively charged electrons, so that it ultimately becomes a plasma. And because of electrical attraction between ions and electrons, they remain very well mixed inside a plasma. So if you consider a volume of plasma, small volume, a volume element, but sufficiently large to have enough number of particles, you would find that it would be nearly charge neutral. There will be equal amounts of positive and negative charges. So you may wonder, then will the plasma behave very much like an ordinary neutral gas? So that is certainly not the case. An ordinary neutral gas is like air, is a bad conductor of electricity, but in a plasma, if you put an electric field, then all the positively charged ions will move in the direction of the electric field, and the negatively charged electrons would move in the opposite direction, giving rise to a strong current. And you all know that currents give rise to magnetic fields, and magnetic fields have Lorentz forces. So these forces act on the plasma. So it's in this field, it's very important to study this interaction between the plasmas and the magnetic fields. And even though the plasma is made up of many particles, ions and electrons, for many purposes a plasma can be regarded as a continuum, just like this air in this room. Even though it is made up of many molecules, so when we study air flow, we often treat the air as a continuum fluid. So when the branch of plasma physics in which the plasma is treated as a continuum fluid, that branch of plasma physics is known by the tongue-twisting name magnetohydrodynamics, abbreviated as MHD. So the basic equations of MHD are obtained by combining the basic equations of electromagnetism and fluid mechanics. So in the afternoon lecture, I shall discuss a little bit how these equations are combined together. So right now, let me only mention about one very famous result of MHD, which is applied very widely in astrophysics. It is Alfvén's theorem of flux freezing. And Alfvén was a pioneer of plasma physics, and he was given a Nobel Prize for his contributions to plasma physics. And one of his most famous results is this theorem. So what is this theorem? So suppose inside a plasma we think of a kind of a hypothetical surface through which some magnetic field is passing. So we have some magnetic flux linked with this surface. And due to flows and motions in the plasma, so suppose the material elements which made this surface, they moved from here to there after some time to make up a new surface, and you would find that there will be some magnetic flux associated with that. And Alfvén's theorem states that if we can neglect electrical resistivity, then this magnetic flux is conserved. So whatever magnetic flux was associated with the surface when it was here, the same magnetic flux would be associated with the new position of the surface made by the same material particles, provided the electrical resistance is negligible. So how negligible it has to be? So in this field, one can define an important dimensionless number known as magnetic Reynolds number. Again, in the afternoon, I shall discuss how this arises. And you see that this magnetic Reynolds number, in the definition of it, this resistivity rho appears at the bottom. So when resistivity is low, this magnetic Reynolds number is larger. And also you see that the magnetic Reynolds number is proportional to L, size of the system. So if the size is large, then also magnetic Reynolds number is large. And this condition for flux freezing is that magnetic Reynolds number has to be much larger than 1. And if that condition is satisfied, then this magnetic flux moves with the plasma. So let me try to explain this further with by giving an example. So you note that magnetic Reynolds number depends on the size. So if for laboratory systems of limited size, magnetic Reynolds number turns out to be much smaller than 1, and in astrophysical systems where L is very large, magnetic Reynolds number turns out to be much larger than 1. So here we can think of a sort of a thought experiment. Suppose you have a chunk of plasma between the pole pieces of a magnet, and we push the chunk of plasma aside. So what will happen in the laboratory situation where the magnetic Reynolds number is much less than 1? Nothing much happens. The chunk of plasma comes here and the magnetic field remains as it is. But in the astrophysical situation where magnetic Reynolds number is much larger than 1, Alfvén's theorem has to hold. So whatever magnetic flux was passing through this region, the same magnetic flux has to pass through this region, and that can happen only if the magnetic field lines take up this kind of a configuration. So in this situation of high magnetic Reynolds number, the magnetic field almost behaves like a plastic material. This magnetic field can be bent and twisted by suitable kinds of plasma motions. And there is a symbiotic relation between MHD and solar physics. There are many solar phenomena which require MHD for explanation. On the other hand, some of the most interesting theoretical predictions of MHD are for high magnetic Reynolds number situations which cannot be tested in the laboratory. So one often says that the sun is the best place for testing many theoretical predictions of MHD, and the subject of explaining solar phenomena with MHD, that is known as solar MHD. Now, just as the Earth rotates around its axis in 24 hours, the sun rotates about its axis in 27 days. But there is one big difference. the Earth rotates very much like a solid body. On the other hand, the sun has what is called differential rotation. In different regions, the angular velocity is different. So it is found that a point near the equator of the sun takes approximately 25 days to go around the rotation axis, but a point at higher latitudes would take more than 30 days to go around the rotation axis. So the angular velocity is higher near the equatorial region. Now we suppose that there is a poloidal magnetic field in the sun. So because of the higher angular velocity in the equatorial region, this middle part of this field line would be dragged more than the other parts, and after some time the magnetic field looks something like this. It is exactly like what we consider in this picture, exactly like that is happening. So you can see that initially there was only a poloidal field, and now after it is stretched by differential rotation, we are suddenly getting a toroidal field inside the sun, which was not there before. So where does this production of the toroidal field take place? Before coming to that question, let me tell you a little bit about what the interior of the sun looks like according to the theoretical ideas. The central temperature of the sun estimated to be about 15 million degrees, and the energy is generated there by hydrogen, by nuclear fusion reaction, in which hydrogen gets converted to helium. And then up to 0.7 solar radius in this region, the heat is transported outward by a process called radiative transfer. And I understand that Professor Shiv Shetty has talked about this process. So it's essentially photons random walk to stellar material. But then from this region, from about 0.7 solar radius to the surface, in this region, theory suggests that there will be very vigorous convection. So in this outer region, this heat is transported by convection, and sunspots are concentrations of magnetic field sitting in this turbulent convection zone. So one question is, why is this magnetic field confined within a sunspot rather than filling up a much larger region? To answer that question, we have to study the interaction between magnetic field and convection, a subject known as magnetoconvection, of which the linear theory was first developed by Chandrasekhar, and then the nonlinear evolution was studied later by Weiss and others. So the basic idea is something like that. Suppose you have a vertical magnetic field inside a plasma which is heated from below, and we know that if the temperature gradient is sufficiently high, then convection will start. But magnetic field lines are known to have tension associated with it, as I shall discuss more in the afternoon. And because of this tension, this magnetic field tries to oppose convection. So eventually, when you make the temperature gradient sufficiently high to start convection, so nature finds it expedient to separate the space into two kinds of regions. In some regions, magnetic field lines are expelled and convection takes place freely, and in other regions, magnetic field lines get bundled up, and because of the tension of magnetic field lines, convective heat transport is inhibited in this region. So the tops of this region become colder than the tops of this region. So sunspots are believed to be such concentration of magnetic fields which are bundled together by convection taking place in the surrounding regions, and because of the inhibition of heat transport by the magnetic field, these regions are colder, and that's why they appear darker. So we believe that magnetic field inside the solar convection zone, probably everyone exist in the form of these kinds of bundle of some magnetic field, which we call magnetic flux tubes. Well, I already pointed out that this a colloidal field line can be stretched by differential rotation to produce this kind of a toroidal field. And certainly this production of toroidal field would take place in a region where there is a strong differential rotation, a strong variation of angular velocity omega. And during the last few decades, as a development of helioseismology, it has been possible to show that there is a strong gradient of angular velocity at the bottom of the convection zone. So here in this region at the bottom of the convection zone, there is a strong differential rotation, and we presume that this toroidal field is mainly produced in that region. And you can see that this toroidal field has opposite signs in the two hemispheres. So if parts of this toroidal field were to float up to the surface, then they will create bipolar sunspot pairs with opposite polarities in the two hemispheres, as you saw in the magnetogram map a few minutes ago. But why would parts of this toroidal field float to the surface? We expect that because of interaction with the surrounding convection, this toroidal field would exist in the form of magnetic flux tubes, and there should be a pressure balance inside and outside. So outside we have only gas pressure, but as I shall discuss more in the afternoon, magnetic field also has a pressure. So inside we have both magnetic pressure and gas pressure and magnetic pressure. So this is the pressure equilibrium equation, and you find that the pressure inside the flux tube would be less than pressure outside. And this usually, though not always, implies that density inside has to be less than density outside. And Archimedes taught us many years ago that in such a situation, if something has lower density compared to the surrounding fluid, it will become buoyant. So this is known as magnetic buoyancy, and in this context, it was first pointed out by Parker. And he also studied this problem carefully, and he found that magnetic buoyancy is particularly strong within the convection zone of the sun, but below the bottom of the convection zone, the magnetic buoyancy can be suppressed. And as we mentioned, that this toroidal field is produced at the bottom of the convection zone. We can think of a magnetic flux tube at the bottom of the convection zone, of which a part has come within the convection zone. So this part which has come within the convection zone will become buoyant and rise to the surface to produce these bipolar sunspots, whereas other parts below the bottom of the convection zone, their magnetic buoyancy is suppressed, and this part will remain anchored at the bottom of the convection zone. So if you want to study the formation of sunspots, then you have to do a calculation of this type. So suppose at the bottom of the convection zone, a toroidal flux ring is produced by differential rotation, and a part of it has come within convection zone. So because of the enhanced magnetic buoyancy there, this part will rise to the convection zone to come to the surface and to produce sunspots. So I and some of my collaborators were among the first people to study this problem through numerical simulations. And it's a sort of an initial value problem in which you have to assume an initial value of the magnetic field inside the flux tube and then let your code go. So at the time when we were doing this work, so all the dynamo theorists at that time told us that the magnetic field inside the sun can be at most 1 Tesla. So we first did our calculations with 1 Tesla magnetic field, but then we found that the effect of Coriolis force was so strong that this rising part of the flux tube moved parallel to the rotation axis and emerged at rather high latitudes, whereas sunspots are lower latitudes. So we found that only if we made the magnetic field much stronger, like 10 Tesla, then only the magnetic buoyancy would overcome the Coriolis force and the flux tube would come in the right latitude to produce the sunspots. And I have also talked about the tilts of sunspot pairs of Joy's law. So one question is that when this part of the flux tube comes to the surface, do we see a tilt produced in it by Coriolis force? So this question was studied by my first PhD student, Sidney De Silva. So here I show a figure from the De Silva and Raichoudhury paper. So this horizontal axis is the latitude, and this vertical axis is the tilt of sunspot pair at a latitude. So this straight line is the best fit to the observational data, Joy's law, that the tilt increases with latitudes. And these various other curves are obtained from our theoretical simulations. So you assume different values of magnetic field in the inside of the sun, and for that we would find out what will be the tilt of emerging sunspot at different latitudes. So we found that if we assume the value of the magnetic field to be 100 kilogauss or 10 Tesla, then only our theoretical results match the observations very well, whereas if we assume the magnetic field to be either weaker or higher, then we could not get a match between theory and observation. So we was rather happy that nearly 3/4 of a century after the discovery of Joy's law, we were able to give the first theoretical quantitative explanation of Joy's law, and at the same time we could put a tight constraint on what should be the value of magnetic field in the interior of the sun. And you people probably know that often the impact of a paper is judged by the number of times it is cited by other authors, and according to Google Scholar, this paper has been cited nearly 600 times, making it the highest cited solar physics paper written completely from India without any foreign co-author. Okay, so as I mentioned that the early dynamo models suggested that the magnetic field inside the sun can be at most 1 Tesla. I shall not get into the explanation of why it was that, and when it became clear that the magnetic field inside the sun is much stronger, 10 Tesla, then only we can match observational data. Then it was clear that these early dynamo models could not be correct, so we needed a new type of dynamo model. So unfortunately, this is a somewhat more technical subject, so I shall not go into the details of this dynamo model. So I shall mention that only by using some ideas which Babcock and Layton developed in 1960s, a new kind of dynamo model could be developed, which is called the flux transport dynamo model, and the foundational paper of this flux transport dynamo is also this paper by me with a couple of my collaborators, and this paper also has been cited more than 600 times. So though I shall not get into a discussion of dynamo theory, let me just make a couple of comments. So as I pointed out that if you have a poloidal field, then by starting from the poloidal field, by using the concept of flux freezing and magnetoconvection and magnetic buoyancy, we could explain many aspects of sunspots. But where does this poloidal field come from? Unless there is a mechanism for producing this poloidal field, it will decay away and the whole process will stop. And because of the oscillation between toroidal and poloidal field, we expect that the poloidal field is also produced from the toroidal field. So the central problem of dynamo theory is to understand how this poloidal field is produced from the toroidal field and how the oscillations arrive. So as I said, that is a somewhat more technical subject, so which I shall not be able to cover in my talks. But you can look at my popular science book where I give a non-technical So even though in this talk I have avoided getting into mathematical equation, for those of you who are interested to know what the equations look like, here I put them in one slide. So the magnetic field is written like this. So this is the toroidal component, and the poloidal component of the magnetic field comes from the scalar function A, and then you can show that from your basic MHD equation that there should be this time evolution equation for the poloidal field and the toroidal field, which are like a pair of couple partial differential equations. So not much can be done analytically. So we developed a code, Surya, in our group to solve these equations numerically, and some of the first results from Surya were presented in this paper in Science. So though I cannot go into the details of this subject, which is a little bit more technical, so let me mention one result which may be of interest to you. So since we have this more solar disturbances, if a magnetic cycle is strong, so we would like to know in advance whether the next magnetic cycle is going to be a strong cycle or a weak cycle. And here I show a plot of sunspot number during the last few years. So the flux transfer dynamo model was evolved around this time, around this sunspot minimum. So this next sunspot minimum was the first sunspot minimum when there were some sophisticated models of the solar dynamo, and whether these models could predict the strength of the next cycle, that became a very important question. So the first attempt of predicting this next cycle, which is counted as cycle 24, was made by Dikpoti and Gilman. So I will mention that Dikpoti did her PhD thesis with me, but then she had been settled in US for many years. So their prediction was that the next cycle will be very strong. So when I read their paper, I felt that their methodology was not correct. So by using our model and another different methodology, we did the calculation and predicted that the next cycle would be a rather weak cycle. And here this circle on this axis shows the time when these predictions were made. And this star indicates what would have been the peak of the cycle 24 according to Dikpoti and Gilman prediction. And this shows what would be the peak according to our prediction. And you can see that the sun almost hit our prediction like a bullseye. So in the history of the subject, this was the first time that an almost successful theoretical prediction could be made of a sunspot cycle from a theoretical dynamo model. And I may mention that our paper was selected as editor's suggestion in Physical Review Letters, which is a very great honor for a physics paper. So it is this symbol which indicates editor's suggestion. And a few years later, another paper from our group also had this honor. In that paper, we developed a comprehensive theory of grand minima, like the Monday minima in the 18th century when sunspots were not seen for many years. So people often tell me that even for professors of Harvard or Caltech, it is very unusual to have two papers selected as editor's suggestion in Physical Review Letter in 6 years. So we are rather lucky that within within a period of 6 years, we had two papers had from our group which had this honor. Well, I have given you some idea about formation of sunspots and dynamo theory, and given an idea of the research from our group. So I began by this talk by mentioning about the solar corona and the solar flares. So in about 10 or 15 minutes, let me say a few words about this outer regions of the sun before I end. So although the sun's surface has a temperature of 6,000 degrees, the temperature of the corona has been found to be of the order of millions of degrees. So how was it concluded? In the beginning of 20th century, some solar astronomers managed to take a spectrum of the solar corona. So which is a difficult job, because this corona is visible only during a total solar eclipse, which may last at most for a few minutes. So within that short time, you have to take a good spectrum. And when the spectrum was taken, it was found that there are some unknown spectral lines. So it was initially thought that maybe this corresponds to some unknown elements which was named as coronium. But by that time, Mendel's periodic table was nearly full, and there was not much room for an unknown element. But then Edlund realized that these are not lines of some unknown element, but lines of iron atoms which have lost many electrons, something like 8 or 10 electrons. And only if the temperature is very high, then only you expect iron atoms to lose so many electrons. So from such considerations, it was concluded that the corona is very high. And this raises an interesting question. You know that according to second law of thermodynamics, heat flows from regions of high temperature to low temperature. But here near the sun's surface, we find that heat is flowing from the surface which is at lower temperature towards the corona which has higher temperature. So is this a violation of second law of thermodynamics? So maybe I shall not answer that question, but leave it for you to think about it to see if you can come up with the answer. And if the corona has really a temperature of millions of degrees Kelvin, then by an application of Wien's displacement law of blackbody radiation, you can conclude that there will be lots of radiation coming from the corona in X-rays and extreme ultraviolet. Now the upper layers of our atmosphere happen to be opaque to this kind of radiation. So even if such radiation is coming from some astronomical source, we can detect this radiation only if we flow detecting instrument, if we fly this detecting instruments in some space mission going above the Earth's ionosphere. And in the last few years, it has been possible to send take images of the corona in this fashion. So here I show you some images of the corona taken in the extreme ultraviolet. So on the left side is an image taken during sunspot minimum, and on the right side an image taken during sunspot maximum. And of course it's not in real time. So the rotation period of 27 days is squeezed to something like a minute or so. And you can see that with the sunspot cycle, the corona looks very different, and the solar surface does not appear somewhat dark because it has a temperature of 6,000 degrees and it does not emit much extreme ultraviolet. So you can see that at the time of sunspot minimum, this corona is full of some bright loops. So these are essentially magnetic loops above the bipolar sunspot pair. So whatever may be the mechanism for producing heat in this corona, that mechanism should be most active within these magnetic loops. So what could be this mechanism? So you all know that when a current flows through a metal wire, it gets heated because of ohmic heating, and certainly this existence of magnetic fields in these loops imply that there must be some currents in the loops. So could these currents flowing through the loops heat up the loops? And another very important result of high school physics, which all of you should be knowing, is that if you send the same current through a thick wire and a thin wire, then much more heat is generated in the thin wire. So when astronomers made some estimates, they found that if the currents in this coronal loops flow through very large regions, then not much heat is produced. But if somehow you could make the currents flow through very narrow regions, then much more heat would be produced. But why should it happen? So the explanation was given by Parker. So his idea was something like this. So you may naively expect that the magnetic field in a loop would look like this, but magnetic field lines are going down below the surface where there is rigorous convection. So Parker realized that this convection would disturb the magnetic field lines, and so instead of looking like this, they would have this kind of a tangle appearance, and Parker proved a mathematical theorem showing that if the magnetic field gets tangled up like that, then current is forced to flow through some very narrow regions in some places, and presumably that's how its heat is produced in the coronal loops, and then the heat spreads around in the other regions of the corona. And we also talked about this solar flares. To explain the solar flares, one has to invoke a very important plasma process known as the magnetic reconnection. So suppose you have a region of plasma. On one side, the magnetic field goes in this direction, and in another side, magnetic field goes in the opposite direction. So by applying Ampere's law of electromagnetism, you can easily show that current density would be highest in this region, and as ohmic heating goes as J square, so we expect that the heating would be maximal in this region. Now suppose in the solar corona there is some magnetic field in some region, and there is some more magnetic flux which comes out from below the surface due to magnetic buoyancy, and suppose the newly emerging magnetic flux has a direction somewhat different with respect to the direction of the existing flux, and if that happens, then you may suddenly have this magnetic reconnection in a very large region of the corona, and giving rise to this very energetic solar flare. So as a result of a solar flare, sometimes large chunks of plasma are thrown thrown out like this, as you see here, and then what happens to these chunks of plasma? And they often move outwards the solar system in the form of what are known as coronal mass ejections, abbreviated as CMEs. So I will mention that this image of CMEs that is taken with a space coronagraph. So a coronagraph is a device in which an artificial eclipse is produced inside a telescope by blocking the sun's disk. But near at ground level, there is so much scattered light that with a coronagraph you cannot see the corona very well from sea level. But if a coronagraph is sent to space, then from that coronagraph you can see continuously you can monitor the corona. So here this image of CMEs are made with such a space coronagraph, and looking at the CMEs, you almost have a feeling that there must be some outward flow from the sun which is carrying away the CMEs. So what could be this outward flow from the sun? So first think of the Earth's atmosphere. You know that the Earth's gravitational field is holding the atmosphere, and imagine what happens if suddenly the temperature of the atmosphere goes up from something like approximately 300 degrees Kelvin, which is now to maybe say 600 degrees Kelvin. Then we know that the Earth's gravitational field will have more difficulty holding on to it, and it will extend much more against the Earth's gravitational field. So when Parker was doing some calculations about the solar corona, he realized that the solar corona is so hot that the sun's gravitational field will be unable to hold on it to it completely. So his theoretical equation suggested that there must be an outward flow of this flow from this outer regions of the corona, which he named solar wind. And when he first proposed this theory, most people thought that it's a completely absurd idea, but within some 3 or 4 years, this existence of solar wind was confirmed by in situ measurement from space missions, and it was found that the density and velocity of the solar wind was very much like what Parker had predicted. So this was considered a triumph of theoretical astrophysics. And you all know that light takes 8 minutes to cover the distance from the sun to the earth, but the solar wind takes about 3-4 days to reach the earth. So and that's why often this effects of solar disturbances are felt on the earth after 3-4 days, because that is the time when the effects of these disturbances are transported by the solar wind. And the solar wind impinges on the Earth's magnetosphere to make it very asymmetric, squeezing it from one side and lengthening it from the other side. Well, I am at the end of my talk, so let me end by commenting this, that a particular scientific field often has a great special kind of aesthetic and intellectual appeal if we can show that various phenomena and concepts of the field are all connected to each other. So in the case of the solar activity, this magnetic field provides a connecting thread. So all these various phenomena we discussed about, they are all connected in a chain of causes and effects. First, the dynamo process reducing the magnetic field inside the sun, and then due to magnetic buoyancy, the dynamo magnetic field comes to the surface and produces the sunspots, and above sunspots we have loops, and the currents in the loops produces very hot corona, and eventually the hot corona drives the solar wind. So one remarkable fact about this field is that it was only one individual, Professor Eugene Newman Parker, who discovered more or less all the connecting parts in this chain of causes and effects. So it was he who proposed who formulated the dynamo theory. He gave the idea of magnetic buoyancy, and he showed how the loops in the corona produce the currents, produce heat in the corona, and it was he who predicted the solar wind. So I had the good fortune of doing my PhD thesis under his supervision. So here I show the building laboratory for astrophysics and space research in University of Chicago campus, where we all work. So this corner room was Professor Parker's office, and this corner room was Professor Subramaniam Chandrasekhar's office, and my office was in this room next to Professor Parker's office. So I was lucky to work in that environment for 4 years. Well, my time is over, and so since this cartoon here more or less captures the essential points which I made in this talk, so I shall leave this cartoon before you to take a look and end here. And if you have some questions, then I shall try to answer. Yes.
So why there is like a temperature loss, a low temperature sunspots?
Well, that I discussed that because it comes from this theory of magnetoconvection, that sunspot is essentially a region where the magnetic field is confined by interaction with convection, and because of the magnetic tension of inside the sunspot, that inhibits convection. So convection becomes much less efficient, and that's why heat transport is less, and that's why these regions are colder and they appear darker compared to the surrounding region. So where convection is taking place in the surrounding region.
Sir?
Yes.
Sir, when the magnetic field is lower, then Joy's law does not hold properly. So what may be the reason for that? I mean, it deviates from
Okay.
increasing.
Okay, so I did not get into the details, but
Yeah,
good
yes,
that you
sir.
have asked this question. So I already pointed out that magnetic field is weak, then Coriolis force makes it go to the very high latitude, and it does not emerge at appropriate sunspot latitude. So that's what we see, that if the magnetic field is sufficiently low, then to have only things appearing in and at rather high latitudes, and there is nothing at low latitude. Yes.
Sir, is there a relation between sun's core rotation and sun cycle?
Sun's
Core rotation and the sun cycle.
Sun's core. So it's a very important question. So what determines the 11-year period of the sun? And it doesn't. And in this dynamo process, the sun's rotation plays a very important role. I could not get into a discussion of it, but there is some other kind of flow in the sun called meridional circulation. I did not want to get into it, but since you have raised this question, so suppose this is the convection zone of the sun, and we know that there is a plasma flow going like this and coming like this. So this is called the meridional circulation, and in this flux transport dynamo model, which some of us developed in that model, this meridional circulation plays a very important role, and the period of the sunspot cycle is determined by this meridional circulation.
So the polarity reverses every 11 years.
Yeah, that's true. That is again is explained by dynamo model, and as I said, that this dynamo theory is a little bit more technical subject, perhaps not too technical. Instead of if I were giving 3 hours of lecture instead of 2, maybe I would have tried to cover dynamo theory, but I thought that in 2 hours it would not be possible. Yes.
So how are faculties different from sunspots?
How are?
Faculties.
Oh, faculae are some bright points on the solar surface. So you would so there's one very important measurement is solar irradiance. So how much energy is coming out from the sun, and usually there are lots of effects near the earth. So these measurements, irradiance measurements, are usually done by keeping instruments in the space mission. And it's a very surprising result that when it was discovered a few years ago, that at the time of the sunspot maximum, the sun is actually brighter. So you may expect that when there are lots of sunspots, the sun the total radiation from the sun would be less. But the total radiation is a very surprising result, that the total radiation of the sun is more when there are lots of sunspots, and still it is not properly understood. So it seems that when lots of sunspots appear, lots of faculae also appear. So maybe the reduction of radiation due to the presence of sunspot that is probably more than compensated by the radiation from the faculae. So certainly faculae are very important and still rather ill understood why they occur and why the sun appears brighter at the time of sunspot maximum. So that is one of the puzzles. Maybe some of you will one day solve this puzzle.
Sir, why cannot we see sunspots in equator of the sun? Is it due to Coriolis force that you have mentioned that northern hemisphere we have?
That is also a very challenging question of dynamo theory. It also comes from more details of dynamo theory.
Sir,
Yes.
another question. So, how does this theory change for like massive stars in which the core is convective but the outer layers are radiated?
Well, in the case of these very massive stars, their behavior is quite different, and this sort of we don't expect this sort of sunspots or solar of these kinds of things in the massive stars. But for more solar-like stars, the stars which are mass similar to the mass of the sun or lower mass. So in these stars also you have a core in which heat transport is radiative by radiative transfer, and then you have a convective cell. So in these kinds of stars also we have this kind of dynamo process, and in some of these stars there is indirect evidence that spots are much larger than sunspots, and some of the flares are much stronger than the stellar flare. So the solar-like stars have stars with mass similar to the solar mass or less mass. They behave very much like the sun, but behavior of the very massive stars, that is quite a bit different. They don't have probably this kind of activities very similar to the solar activity.
One more doubt. So, since we have the number of solar spots data for almost 400 years,
Yes.
can we use this data to figure out or use simulations on how many solar spots we can see in the upcoming cycles?
Okay, so first of all, I should tell that now we have not only for 400 years we have actual records of observation, but for about past 11,000 years now we have some idea how sunspot number has varied by indirect method, because when there are more sunspots, the magnetic field in the solar wind is stronger, and then less number of cosmic rays come, and these cosmic rays produce some radioactive the radioactive isotope. So from the study of radioactive isotopes, it has been possible to figure out how the last 11,000 years how it has happened. So explaining that this data of last 11,000 years, that has been a big problem, and I mentioned this one paper from our group which was selected as editor suggestion in PRF. In that paper we studied this problem. And coming to the question about future sunspot cycles, so you know that there is quite a lot of research being done, and my own point of view is that in a sunspot, I did not get into details of the dynamo process, but in the dynamo process it's a complex combination of various processes, and I believe that some of these processes are deterministic and some are completely random, and you cannot predict them. And my point of view is that when a sunspot cycle decays, it is more like it is dominated by more deterministic processes. But when the sunspot cycle rises, it is in that phase when it reaches the peak, it is more dominated by these random processes. So in my view, and with which many other colleagues agree, that only this phase of the sunspot cycle is somewhat predictable. So by studying from various indicators at this time, you may be able to predict what will happen, what will be the strength of the next cycle. But after that, it goes through a phase where things are governed by random processes, and predictions are no more possible. So my point of view is that you can, no matter how much theoretical advance takes place, will be only able to predict the next cycle around this time when the sunspot cycle starts decaying, but you will never be able to predict the cycles after that. But there are many other people who do not agree with me. They try to predict next 5, 6 sunspot cycles, and in the past all these predictions turned out to be completely false, but still some people by various methods keep on trying to make such predictions. Yes?
You mentioned that there is a process which converts
is not differential. It is a, as I said, that is a more complicated process. So it involves convection and it involves this Coriolis force. You know that in the Earth's atmosphere, because the Coriolis force, we have these cyclones and anticyclones which also rotate in the Earth's atmosphere. So in the sun also, in the convective motion gets affected by this sort of Coriolis force, and we have things like cyclones and anticyclones. So some of these things are involved in converting the toroidal field to a colloidal field. So that's why it's a more complex process. So I discuss this production of colloidal field from the toroidal field, which is the toroidal field from the colloidal field, which happens due to meridian, due to differential rotation, which is a more simpler process because of it's a direct consequence of Alfvé's theorem of flux freezing, but the opposite is involves this sort of cyclonic convection in the sun's convection. So it's a more complicated process. Again, as I said, that instead of 2 hours, if I had 3 hours, then maybe I would have tried to explain it, but I decided to keep this out of these lectures. So any other questions? Okay, then maybe we shall break for tea. There should be, I suppose there should be some tea outside.